Now we're going to turn the time over to Zach, who you also know very well. And Zach now works at Area I for Nick Alley.
Okay.
He just started there. What was it, Monday, Zach?
Yes. Yep.
Okay,
I've been
so,
here 3 days. Today's my 4th day.
so they've been kind enough to let him zoom into this meeting to present his work. So
Okay.
And I unfortunately, thank you. I unfortunately can't turn on my camera. I'm not allowed. And my desk right now is pretty close to the break room here. So if it gets a little bit too noisy, just let me know and you can take over, Dr. Hunsaker. Is Brian Holmhansen not there?
no, his plane his flight got canceled, and so he'll be here at noon today.
Oh, that's unfortunate.
So we're recording this for him. Yeah.
Okay. Alrighty, let me share my screen. Can you guys see my screen?
Yep.
All right, so these are slides from my defense. So you've already seen these, James. So this title's a little off from what I'm going to be talking about. We are looking at the optimal lift distributions that will minimize induced drag during lateral maneuvers. So during rolling rates, when we want to generate a rolling moment, things like that. I'm not sure how much of a review of lifting line theory Jeff went into or what was done previously, but for this section, it's very helpful to have a little bit of review on lifting line theory to understand what we're talking about. So lifting line theory was the first method to be able to accurately predict lift and drag on a wing. It models a wing as a vortex filament and a trailing vortex sheet. And so we'll have like a trailing, we'll have a vortex filament on the lifting line of the wing, and then a trailing vortex sheet, which would model the wake behind the wing. And the main hypothesis of lifting line theory is that the lift at any two-dimensional section along the wing is equal to both the vortex lifting law, which you can see on the left-hand side of that equation, and to a linear airfoil theory, which just assumes that lift varies with respect to angle of attack in a linear relationship there. And there's basically two unknowns with this equation. We know the full geometry of the wing. The only thing we don't know is the vortex strength along the lifting line. And we also don't know the induced angle of attack that's caused by the wake behind the wing. But we can relate the induced angle of attack at any section along the wing as a function of the vortex strength along the wing. And if we do that, we get this fundamental lifting line equation, which, as you can see, is pretty hairy. It looks kind of nasty, but there's only one unknown here, and that is the vortex distribution across the wing and its derivative. And so we can obtain a solution to the lifting line equation by assuming a general form for this vortex shape or for the vortex distribution. And to do this, we do a little bit of change of variables. Our span-wise coordinate changes from z to this theta, but we have this infinite Fourier sine series that we assume the vortex distribution takes that form. And if we do that, we can get a tractable solution to lifting line theory. We have to first truncate the infinite series. And then once we do that, we can substitute in the value for the vortex distribution and its derivative into the lifting line equation, which can simplify down to just this equation right here, which we can evaluate this at n different locations along the span, which allows us to solve for the n unknown Fourier coefficients. So after we do that, we can solve for all the Fourier coefficients. That means we can solve for the vortex strength, and then we can solve for the lift distribution that way. After we've solved for the lift distribution, we can integrate that to get our net lift, our net drag, our rolling moment coefficient, and our yawing moment coefficient on the wing. And then we can non-dimensionalize those to get our traditional aerodynamic coefficients, which are shown here on the left. The lift coefficient is one thing to note here that's very interesting. The lift coefficient is only a function of the first Fourier coefficient. And the rolling moment coefficient is only a function of the second Fourier coefficient, which is very interesting. The induced drag and Young moment coefficients, however, are a function of all of our Fourier coefficients. Included in here are the effects from rolling rate, which is this p-bar variable here. Using these Fourier coefficients the way we have, it can be a little bit, difficult because for any small change in geometry, any small change in orientation of the aircraft or twist, we have to repeat the entire analysis. Instead, we can decompose the effects, or we can decouple the effects from the orientation of our wing or the overall angle of attack. We can decouple that from the wing twist and from the rolling rate of the aircraft. And if we do that, all of the Fourier coefficients are decomposed into these smaller Fourier coefficients, which depend only on certain aspects of the geometry. So you can see that here. One thing to note, the odd Fourier coefficients correspond to spanwise symmetric effects. So planform is typically symmetric on the wing. The right and the left wing look the same. And so that's typically corresponds to an odd Fourier coefficient. We can break up components from spanwise symmetric twist and spanwise anti-symmetric twist, which we've done here. And then we can see the effects from rolling rate, which affects the wing anti-symmetrically. So we could do this. That simplifies the analysis quite a bit. And then it also allows us to help find optimal lift distributions. So one of the goals of this project was to determine which lift distributions or twist distributions will minimize induced drag during a rolling maneuver. And so the first case we consider is roll initiation, which is when there is zero rolling rate, but there is a non-zero rolling moment. And so we have a rolling moment constraint, right? So our second Fourier coefficient is constrained based on our desired rolling moment coefficient. Since there is no rolling rate, this term right here in the induced drag equation drops out. And so we can see here, if we want to minimize drag, we want as many of these Fourier coefficients to drop to zero as possible. And since we're only considering anti-symmetric effects, we're only considering the even Fourier coefficients here. And so what we want is all of the even Fourier coefficients to go to zero. However, we can't let the second Fourier coefficient go to zero due to our rolling moment constraint. And so in order to ensure this right here is the anti-symmetric twist distribution needed for any plan form in order to achieve this. We've broken up this anti-symmetric twist distribution into like a normalized shape, a normalized distribution, which is dependent on like the core distribution of our aircraft and things like that. And then that normalized shape would be dimensionalized. It would be scaled up based on our desired rolling moment. This plot on the left shows what that normalized anti-symmetric twist looks like. That will provide the optimal twist or the optimal lift for a roll initiation case. And I've only shown one wingspan here for our normalized twist distribution. I've showed for various rectangular wings of various aspect ratios what that looks like. Then I've also included on here what it would look like if we had an elliptic planform. And very interesting here, if we have an elliptic planform, the shape of our twist distribution is just going to be a linear variation in twist. We want the twist to vary in a linear fashion from the root up to the tip for elliptic planform wings, and that will generate minimum induced drag during our roll initiation maneuver. The second case we considered was a steady rolling rate. So this is the case when the rolling moment coefficient is zero, but the rolling rate is non-zero. And so again, we can see since the rolling moment coefficient is 0, A2 has to be 0, which causes this first term right here to cancel out in our induced drag equation. And again, we can see for this case, we still want all of our Fourier coefficients to go to 0. If we could design it like that, then we would be at the optimal case for a steady rolling rate maneuver. And essentially what we want is our anti-symmetric twist distribution to negate the effects from rolling rate is what this turns out to be. And so we want our twist distribution to negate what happens during a steady rolling rate. And since a rolling rate has a linear change in angle of attack on the wing, we want our twist to be a linear change as a function of span. And this equation right here is what would do that. But then we just do it in the opposite direction of our rolling rate. What this means is, regardless of wing plan form, the anti-symmetric twist to minimize induced drag during steady rolling rate is going to be a linear change in twist. It doesn't matter what plan form you are, that's what it's going to be. And because of that, I haven't plotted what those look like. I've instead looked at here, if we were to use an elliptic plan form, and if we were to use this steady rolling rate optimal twist for a steady rolling rate maneuver, how does that affect our roll-yaw coupling, our yawing moment to our rolling rate ratio? And it turns out for various taper ratios and aspect ratios that the yaw to roll coupling is always negative. What this means is we will always have an adverse yaw associated with this rolling rate maneuver. If we were to use a no symmetric twist, but use this optimal steady rolling rate twist. And similar results were found for the roll initiation case. If we were to use no symmetric twist on various tapered plan forms with various aspect ratios, we always get a negative yaw corresponding to our roll maneuver. We always get adverse yaw for those cases. The third maneuver we considered was the transient period between roll initiation and steady rolling rate. This would be the case where we have a non-zero rolling moment and rolling rate. And it turns out that the optimal solution here is just a linear combination of the previous two, which you can see here. And then we were able to validate these analytic results using a numerical nonlinear lifting line method called mockup, combined with a nonlinear optimizer routine, where the optimizer used mockup as its cost function, and it was able to change the twist distribution along the wing to try to minimize induced drag while meeting a given roll maneuver constraint. And you can see that the computational results from this numerical validation study fall right on with what we predict with our analytic method, which this gives us a lot of confidence that what we have is correct. So that was the kind of the first part, and we have a journal paper published on these optimal twist distributions. The next is considering how roll-yaw coupling takes into effect. We found from these optimal twist distributions that if you don't do anything with the symmetric twist, you will always get adverse yaw. So now consider what happens if we use one of these lift distributions within the B3 class, as Jeff defined it earlier. What is the optimal anti-symmetric twist distributions we need to control roll-yaw coupling but still minimize drag? Towards this goal, we define a couple of roll-yaw coupling ratios. One can be associated, you could think of it as being associated with roll initiation, and another with a steady rolling rate. which is essentially just the ratio of the yawing moment to the rolling moment, all normalized by the lift coefficient. So if we were able to solve for the optimal antisymmetric twist distribution that will minimize induced drag for a given B3 class of spanwise symmetric lift distributions and for a desired rho-yaw coupling. So for a certain rho-yaw control ratio and for a certain B3 value, we know what the antisymmetric twist distribution needs to be, and it's defined by these equations right here. This plot on the left shows if we were to use this for the given B3 lift distribution, if we were to use these antisymmetric twist distributions, how does that affect our induced drag? These contours are a percentage increase in induced drag compared to the absolute minimum induced drag for an equivalent rolling maneuver. And so you can see for a B3 lift distribution of minus 0.3 and for about neutral, or if we have neutral rho-yaw coupling at a B3 of 0.36, 0.37, we're going to have about 40% increase in induced drag, as we otherwise would during that rolling maneuver if we did not consider yaw. We were also able to derive closed form expressions for the B3 value that would minimize induced drag for a given rho-yaw control ratio and vice versa, the rho-yaw control ratio that minimizes induced drag for a given B3 when we use this antisymmetric twist distribution. The next case we considered is for steady rolling rate. This is very similar. So this equation is very similar to what we found on the previous equation. We found the antisymmetric twist component that will guarantee a certain rho-yaw coupling during a steady rolling rate. This antisymmetric twist distribution needs to be added to the previous antisymmetric twist we found previously that negated the effects from rolling rate. And so this would be the total antisymmetric twist distribution you want to use. And again, this contour plot shows the percentage increase in induced drag if we were to use this during a steady rolling rate maneuver compared to the absolute minimum induced drag we can achieve for a steady rolling rate. And you can see for neutral rho-yaw coupling, you would want to have, in order to minimize induced drag, you'd want to have a B3 value of about minus 0.4, and that would correspond to a percentage increase, I think, of about 77% greater than what you would have if you did not consider yaw effects. So controlling rho-yaw coupling from the main wing can come at a pretty high cost to induced drag. This right here, I'm not sure if we have time to go over it, but I considered, what if we don't limit ourselves to the B3 lift distribution? What if we use all of the Fourier series and try to use that for controlling rho-yaw coupling, or just to generate a yawing moment? And not to spend too much time on this, but if you want to generate a yawing moment without any rolling moment, so for the special case of no roll, the minimum amount of increase in induced drag caused by the yawing moment is equal to twice of the magnitude of the yawing moment. And I was able to verify that numerically. And as I refined my estimate, as I retained more coefficients from the infinite Fourier sine series, my prediction approached this assumption exponentially. This assumption that this increase in induced drag is equivalent to using a point drag force on the tip of the wing, which kind of leads towards the idea of using drag devices out of the edge of the wing to control yaw for the main wing, which is very similar to what the B2 Spirit, the stealth bomber, does with its split flap ailerons. They act like a drag device out of the wingtip, and that's one of the most efficient ways you can control yaw on a main wing. Any questions?
So Zach, so I know that you optimize for drag for all of these cases, but the yaw and rolls, especially like a B2, the configurations, they don't want to turn too much because maybe that's the case when they are kind of captured by the radar. So most of the time they're wanting to kind of fly, kind of loiter or something like to fly straight. So
You mean they want to fly with wings level?
yeah, so I was curious, so maybe if we are wanting to look into the roll and yaw, then why not optimize for the roll performance or yaw performance or something like that rather than drag? Was there kind of, can you remind me why you
So the
optimize for drag in this kind of conditions?
so the roll and yaw. So it doesn't make sense to optimize for roll or yaw. Those are your constraints to your problem, right? That's what's required for the flight mechanics for your particular trajectory or path you want to follow. That would be a requirement. If we were to optimize for yaw, like I've done that, I've optimized for yaw, and all that does is gives you the max yaw authority that you can achieve with your setup. That's all that will tell you. So it is beneficial in that sense to know your max authority, but for any condition away from the max yaw setting, say you only want to implement 10% of your yaw capabilities, you want to you want to be able to do that optimally, and by optimally we mean with the least amount of drag possible.
Right, so probably I didn't ask the wisely, but so for the yaw and roll, those are kind of instances. So they are not the flying all the time with the roll or yaw, but you are optimizing for drag for those conditions. So I was kind of curious whether it makes sense to use drag as an optimal optimization objective of the optimization rather than other kind of metric in this case.
We have looked at other metrics, like trying to minimize the amount of control surface deflection, things like that. So we have looked into other things like that. What I would say is I've run thousands upon thousands of optimization cases for different roll yaw maneuvers. So I found the optimal twist that will minimize induced drag for any arbitrary roll or yaw maneuver, which is kind of what we were going here with these analytic solutions. It doesn't matter what the roll or yaw maneuver is. We have a closed form solution that predicts what the minimum induced drag is, or what the optimal solution is for that maneuver. I don't know if that answers your question a little bit.
Yeah, so actually, I don't know the answer either, so I'm kind of curious, and I just wanted to remind myself. So I was kind of working with you on this problem, but yeah, so I was kind of curious. And also, going back to the page 15, and was there a reason that you put that the figure on the right?
So I didn't talk
the
about this
left.
very much because Jeff already talked about it a little bit. This is just an animation showing that
Right.
B3 class of symmetric lift distributions. It goes from B3 which is the elliptic, up to B3 minus 1/3, which is Prandtl's 1933 bell shape. We use some B3 values that are outside of this animation. Like right here, the animation goes from 0 to minus 1/3. But you see here, we go up to minus 0.5 in this figure. So sometimes for yaw maneuver, for roll yaw control maneuvers, you might go beyond the bell shape to something a little bit past that. But we've only really considered here all the negative B3 values. Oh, and one thing I should note, and a very important finding of this analytic work that we found, is that if you're operating at a B3 value of 0, which means the symmetric component of your lift is elliptic, there is no anti-symmetric twist distribution you can come up with that will control roll yaw coupling. So roll yaw control, roll yaw coupling control is only feasible when the span-wise symmetric component of the lift is not elliptic.
So you have to move away from the elliptic lift distribution in order to control roll yaw coupling.
Exactly.
If you have an elliptic lift distribution, then you will always get adverse yaw. So we have to move away from the 0 there in order to control the roll yaw coupling.
Any other questions?
So do all these optimizations like feed into the horizon control algorithm?
So I'll get into that later, but all this is the analytic work. There were some numerical studies done here to kind of validate the analytic stuff, but I will get into that later today.
This almost defines like the goals, like if each condition, depending on what you're trying to do with the aircraft, these are kind of like your optimal.
Yeah, so these would be like the absolute optimum we could design to head if we had infinite degrees of freedom on horizon. This would be what we want to do.
So another stupid question. So adversia and proversia. So it is. So actually, you're turning to the same direction, but do you need a different controls? So maybe the pilot will feel different, but otherwise, is there some kind of other benefit or something?
Yeah, so if you want to turn to the right, you usually bank the aircraft because your lift is the largest aerodynamic force, right? You want to use that to accelerate yourself to the right. Right. So you bank the aircraft to the right, but the aircraft naturally wants to yaw to the left. That's adverse yaw. And that's what we're showing here. If you have an elliptic lift distribution and you deflect the ailerons, doesn't matter where you put those ailerons, how it's designed. If you have an elliptic lift distribution and you deflect the ailerons, you will always get adverse yaw. So the aircraft's going to want to yaw the opposite direction that you're trying to turn.
Okay.
So what we do right now on the Spitfire or any aircraft, basically they mix in the rudder to cancel out the adverse yaw. But that was the point of Al Bauer's work, is he said, look, if we have a bell-shaped lift distribution, we can deflect these ailerons and it will actually give us proverse yaw. So we don't need a rudder to counteract the adverse yaw. And so when we bank right, the aircraft will also yaw right. Or you can also design them so you get 0 adverse yaw, meaning the aircraft doesn't yaw at all. You know, so there's a special location you can put the ailerons to do that.
So those are kind of already taken care of by some different control surface, adding more other control surface there.
Yeah.
So it is kind of taken care of by some different controls.
Yeah.
But what's the other benefit? I mean, so by developing this to generate the proversia capable, so you wanted to control the location of your aileron, or so what kind of other kind of benefit that you can expect when you develop the proversia vehicle? capable vehicle.
So it just,
Maybe get rid of that, the
Yeah,
rudder,
that's
that's
exactly right.
another one.
So you get rid of the need for the rudder.
Right.
Because you don't need to coordinate the turn, basically, or you don't need to,
That's the main.
that's
kind
the
of
main thing, yeah. Yeah. So it's that, because on a lot of aircraft, they have the aileron. The linkage system is actually coupled, so when you put an aileron, it automatically
Yeah.
deflects the rudder
Right.
to take care of this exact problem. But if you don't have adverse yaw, you don't need the rudder deflection necessarily. There are other reasons that you would still want the rudder deflection, but one of the reasons is adverse yaw, and we're getting rid of that. So
Would it affect your turning radius?
it depends on if you're trying to coordinate the turn. So that's another reason. And sometimes people mix these two, and I guess I'm not sure that it's the same thing. I don't think that it is coordinating the turn and zero adverse yaw.
Yeah.
I'm almost certain those are two different things. So we're able to get rid of the adverse yaw, but you'd still need it to coordinate the turn theoretically. Yeah.
Dr. Unsaker, was that drag relationship the one that we talked about in my proposal defense? The one that Zach just showed that we want to look at the minimum?
Oh, yes,
Okay.
yes, yeah, that's right.
So then all the tailless aircraft, Proversia capable, so like a B2.
Yeah,
It's-
but see, it's using split flaps to control yaw.
Right,
So yes, so when it banks, it's also mixing in some of the split flap.
Right.
To create Prover's yaw. Yeah. Because otherwise it would just get adverse yaw, but if it didn't,
Right, right.
Mix in some of the flaps.
so then how can this Zach's work can be kind of benefit that kind of control?
So it's a good question. So let me drop on the whiteboard for a second. Thanks, Josh, for joining us. Josh is the next presenter. So if we have so I'm guessing that the B2 is using something close to an elliptic lift distribution, but I don't really know.
Right.
So anyway.
I need to run down to the lab.
There we go. Okay, so let's say the B2 has an elliptic lift distribution on it, and then it deflects its ailerons to roll. Well, so that's going to create a little extra lift here and a little less lift there, whatever, right? But so that it's rolling the aircraft, but it's also creating this adverse yaw that has to counteract. So then it's also going to open up its split flaps over here in order to counteract that adverse yaw, right?
Right.
But what we found is if the B2 was carrying the elliptic lift, the bell-shaped lift distribution, or actually any other lift distribution than the elliptic, right? But the bell-shaped is a common one. There's actually a location where you can put the ailerons out here where it naturally creates Prover's yaw. You don't have to split your flaps anymore to get rid of the adverse yaw. It will just naturally produce Prover's yaw. Does that make sense?
Then let's apply that to the parental D aircraft to
Yeah.
there.
Yeah.
So then, but parental D, as you said, mentioned, it is kind of the one point,
Yeah, that one lift coefficient,
Right.
they can hit the bell shape.
right? So then if we can do that all the time, then that makes sense to have that, the
Yeah.
parental viewing and doing that.
Right.
But if it has only one
Yeah,
kind of specific point, then anyway, it also need to have that the split kind of aileron.
possibly. So when I say at one point, I'm saying, let's say that this is the exact bell-shaped lift distribution, right? And they can only hit this at a certain velocity.
Right.
But if they're during takeoff, they're not at that velocity, or maybe they're gonna, throughout most of their flight, they're assigned a different one. So they're at a slightly different, I don't know, they're gonna be at a different lift distribution now. But still, they can get Prover's yaw over their whole flight envelope, as long as they never hit the elliptic lift distribution.
Right.
Does that make sense?
There's a range though, right? Like there's a
Yeah.
range of,
Locations where they can
Yeah.
have their aileron
Yeah.
here, that's still gonna give them progress yaw. So they can still get progress yaw over the whole flight envelope. We're just saying that technically speaking, they're only hitting the bell-shaped lift distribution at one flight condition, although they can be close to it at other flight conditions. So they can still get progress yaw based on their aileron design. They can get better with their whole flight envelope, but their lift distribution is not gonna be perfectly bell-shaped except for one.
So then the buyer, so when we control that, we are get rid of the rotor back
Yeah.
there. So we are kind of experiencing a hard time because we cannot create those bell shape.
Right. But the buyer, we're gonna have a control surface back there that can still they can still take out adverse yaw. When we, yeah, so the buyer, we're just gonna use our rudder, a different kind of a rudder.
Right.
To do it. Yeah, so it's okay that we can't, it's okay that we're gonna have to get adverse yaw on the buyer, that's fine. Cause we'll take it out with the tail.
But it could have been much easier if we can
Oh,
generate
yeah.
the bell shape for the main wing.
Right, then we would need less rudder, right?
Okay.
Yeah.
and some of the stuff that we've seen also shows that maybe that coefficient is smaller when you don't have the vertical tail back there. So that might be another benefit, is we need to counteract less adverse yaw. That's something that CPA analysis kind of showed us, was we have less of a correlation between those two. So we might need less yaw than a traditional aircraft. Yeah, and they've talked about that with birds too. So actually, I think Al Bowers was looking at this because of birds, because they fly at a certain, when they're in formation flight, they fly a certain way. And so that's why they came up with that.
Yeah.
And can we make the body more aerodynamic so that it can have kind of higher lift
In the middle?
geometry in the middle?
Yeah,
And then it will be much easier.
yeah, so you can go to a blended body type of idea and control that lift and actually Horizon here is kind of that shape, although that wasn't the point of doing it that way, but yeah, you could actually blend the body, so you can get this lift distribution by simply twisting the wing again, right? So how you design the twist in the wing, and that's how Al Bowers is doing. They have twists across their wing so that it creates more lift in the center, simply because the center of the aircraft is at a higher angle of attack than the tips, right? So it creates this bell shape. But you can also do that by changing the shape of the body. Okay, and having more a larger chord at the center that naturally produces more lift at the same angle of attack as everything else. So you could, I suppose, design an airplane that has kind of this shape of a blended body wing or something, and it's all roughly the same angle of attack, but it creates this kind of a lift distribution. So, in fact, we have a paper on that. A journal paper on that, on how to design the chord distribution. If you have a certain lift distribution trying to get, you can design the chord of the wing to produce that lift distribution. And zero twist or whatever. So